Did you need any additional memory for this one?
I've been swapping the. I'm taking the card out of this one and downloading it onto my big jump drive, and then also downloading it onto the computer.
Okay.
So that's in 2 spots, and then I clear that one off.
So this one is good for probably 2 hours recording or whatever.
Yeah. But that's just with that one card. I've got a card in my office that's mine that'll hold hours upon hours. That's huge.
What's the size of memory card?
That one's a 2 gig.
Only 2
Only
gig?
2 gig. Yeah, but the one that we have that's for it is a 32 gig.
Okay.
So we have one that'll take a lot of hours, but it's got all my cap videos on it. I didn't want to take a chance of messing one of those up. There he is.
So hey, no muffin for us?
Nah, no muffin for myself.
Next time, okay, if somebody's late, we should not whip him, but let's say $1 per minute. How about that?
That'll work.
That'd have been expensive.
$15.
Actually, that would have been $14. $12.
Okay, next time. Where's Alex? Maybe in the restaurant.
Did you see him in the hallway?
I was booking.
Should be in the restaurant, I guess.
I had to walk 15 miles to get here.
For the faculty meeting in the department, previously quite frequently somebody was late and then another body was late again. Then we tend to set up a rule. Okay, whenever whoever is late 1 minute, $1 penalty. We talked about that and I thought, hey, it's a good idea. So actually that day I was about 1 minute late. I put $1. Then that became the rule. And then what happened is nobody's really late. Yeah. Liquefaction. Objectives.
Don't be late.
Okay, again, from the next class, whoever who is late, okay, $1 per minute. Then please be late.
Yeah, who does the money go to? Do we split it up amongst people on time?
Maybe we can buy some muffin or coffee or whatever.
Yeah, some donuts in the
donut.
How about that? Every day somebody go to Shipley's and bring a dozen donuts and we'll rotate it.
That'll work. You're first.
Need to
Eat them half of them.
know whether the soil will liquefy or not. Li2U. That means we are the geotechnical engineers and you will claim that you learned soil dynamics from Dr. Chung. And people will expect that you know how to figure out whether your soil will liquefy or not. This topic is also called evaluation of liquefaction potential. That is very, very important. The whole reason why you learned about earthquake is really to figure out the liquefaction potential of our soils. Liquefaction mechanism. This is the mechanism that we already talked in the previous class. It was something like this one. We have saturated soil Okay, this kind of condition. Okay, there should be water, 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 water. Okay, when we have earthquake motion, this way motion, and those guys can move this way, and this guy can move this way, and then it will tend to change its condition or configuration something like this way. When you compare this void space and that void space, we can know size of the void tend to decrease, and it will cause core pressure build up. Then we know that effective stress is total stress minus core pressure. When this core pressure is going up, then total stress will stay constant. Then this guy will go down, and eventually the magnitude of this effective stress will be almost zero. Then again, for the sandy soils, we know that strength parameter or Moore Coulomb's failure criteria is C prime plus sigma prime tangent P prime. Again, for sandy soils, this guy will be virtually zero, and it will be sigma prime tangent P prime. Then when this guy, our effective stress becomes about zero, then when this one becomes about zero, then this guy will become about zero. When shear strength becomes about zero, then means liquid. Okay? That is the reason why we call it liquefaction. Again, liquefaction does not mean our sand particles will become the liquid. That means behavior of the saturated sand will be very similar to the behavior of the liquid. Okay. Then okay, this one is the fundamental mechanism of liquefaction. Then what's going on in real field is this one. Real earthquake vibration and liquefaction. Okay. Let's say this one, this y-axis is earthquake vibration. Let's say this one is normalized or regularized earthquake vibration using the technique that we taught in the previous class. Okay. Then, what happened to the core pressure is?
It's increasing over time.
Yeah, let's say this one is just delta U. We will just forget about the initial core pressure. You like boxing?
Yeah, back in the old days.
Okay. Let's say, probably you remember the guy named George Foreman.
Mm-hmm. Who makes the grill now?
Yeah, he makes the grill now. Yeah. Do we have one?
No, I
Yep,
don't.
I got one.
Is it really good?
Yeah, it's not too bad.
Okay.
Can't put a Can't put a
Maybe-
big piece of meat on it, but it's
Maybe I will get one. I don't know how come. I think he really does not make the grill, but he is trying to just sell those things, right?
Yeah.
yeah, he's just a spokesman.
But we know that he got a big punch. Okay, I guess his really killer punch is uppercut or hook. Okay, for his punch, probably one blow will just kill us. Then let's say poor Jimmy is on the ring with George Foreman.
I'll show him the ropes. Oh, 1, 2.
Okay, then probably the only way he can win, he can beat up George Foreman is if Jimmy can hit, let's say, 50 times before he was hit. Probably he can knock down George Foreman. Is that correct? Okay, so
I'll say yes.
the rule is this one. Even though, let's say, Jimmy's punch is not strong enough, if he can just accumulate the damage to George Foreman's chin, then damage will be accumulated, and finally he will knock out. Same thing for the earthquake vibration. Okay, some earthquake vibration, the motion is really strong, then probably one cycle will just destroy everything. But in real life, that kind of earthquake is very rare. Okay? But most of popular earthquakes are something like the Jimmy's punch. That means with the first cycle, it will increase the pore pressure something like this much. Not too much, so our soil will not be liquefied and our structure should be okay. So one cycle. Then after first one, then second cycle is there. Then our excess pore pressure will be increased a little bit more. So it will go up this way. Then with the third cycle, with the third hit, pore pressure will be increased a little bit more. Now you can see the damage is accumulated, right? In this figure, pore pressure is accumulated. Somewhere here, let's say, somewhere here. Let's say at this point, pore pressure is high enough so that our total stress may be 0. Okay, somewhere here, let's say, our total stress is almost 0. That means our soil will be liquefied after fourth cycle. Okay, again, that means liquefaction is there. Even the magnitude of our earthquake may not be very high. At the same time, we can say, let's say with the magnitude 9 earthquake, our loose sand can liquefy immediately. But with a magnitude 8 earthquake, if we have, let's say, 10 cycles, then our soil can liquefy. With a magnitude 7 earthquake, we may say, wow, with the, let's say, 50 cycles, our soils can liquefy. Okay? We can say soils can liquefy with accumulated excess pore pressure. Okay. So far I said somewhere here silty sand, somewhere here just soils. Even though I just said soils, usually it should be sandy soils. That means clayey soils do not liquefy usually. How come the clayey soils do not liquefy?
Because of the shape of the particles.
Shape of the particles?
Because it don't allow for such high void ratio.
Well, it's close, but really not the direct answer. What did you say?
It doesn't have the pore spaces between the particles in this.
Pore space is there in clayey soils.
It's not as
Okay. Anyway, anyhow, the clayey particles of clayey soils should be different from particles of sandy soils, right?
They're flat.
Hmm?
They're flat.
It's
Not as
usually
much.
flat or needle shape. Let's say we have clayey particles, and by earthquake vibration, there should be relative movement, right? First of all, size of those particles are, even though I plotted those particles about this size, actual size of those particles should be a lot smaller than sand size. So the first thing is relative motion or relative displacement between those particles are a lot lower than those in the sandy soils. So the actual particle displacement is lower. And another thing is, think about the modulus of clayey soils compared to the modulus of sandy soils. Which modulus is high?
flat.
Maybe the dry edge clay has very high modulus. Saturated one, think about the saturated clayey soil somewhere in New Orleans. They are very weak, right? Again, liquefaction is for saturated soils. But usually the modulus of those clayey soils, especially modulus of those particles of clayey soils, are a lot lower than this one. That means when there is some stress built up, those clay particles will deform very easily. Something like this one. Okay. Plate shape. When there is some stress, they can easily bend. This one, let's say sand particle. When there is the stress, they will try to resist. Okay. So whenever there is the internal stress, those particles try to bend or elongate it. They will try to rearrange their configuration very easily. So many times, those clayey soils will absorb earthquake vibration internally. That's the reason why they don't liquefy. Okay. And gravel soils. We don't say they will never liquefy, but many times we will say gravel soils is the one that we don't have to worry about the liquefaction. Why?
Because their void ratio is
So high.
large.
Whenever pore pressure tends to build up, then they can dissipate so quickly. So this pore pressure will not increase substantially for gravel soils. Okay. When you read some articles published sometime 80s and early 70s, you may see some people claims that they have the clayey soils, they have the gravelly soils, those soils liquefied. But nowadays, we usually say that the liquefaction for gravel soils or clayey soils was the experimental error. Okay. Then I will talk about how do we really check whether our soils will be liquefied or not. Do you see a red pen? See it. That's fine. It's in my pocket. to actually reproduce the liquefaction, many times people use so-called cyclic triaxial test. Cyclic triaxial test is this one. We have triaxial sample. Usually what we do is we apply confining stress to our triaxial sample. Which symbol do we use for confining stress?
Sigma. There'd be 3.
3, or sigma C. Short C means confining. Then we have, okay, sigma 3 is the usually hydrostatic pressure, so it should be all-round pressure. And traditional static triaxial test is the one that we consolidate or we just apply this kind of confining pressure. And to fail the sample, we apply additional stress along vertical direction. Is that correct? Traditional triaxial test. Oh, it's T. And then let's think about dynamic condition. Dynamic condition should be this one. Okay. We should have initial confining stress. For the second figure, we should have the arrow on both sides. Okay, think about this condition. I said false dynamic triaxial test. That means something is wrong on this mechanism. Okay. Your sigma 3 is there, and you apply dynamic or oscillating vertical stress. It looks like that is perfectly fine, but okay, let's say this one is the soil, this one is the soil, all those are soil particles. This is the loading mechanism, and I will apply oscillating stress, compression, tension. Then tension will probably take out the soil particles, or Anyway, compression, tension. At the moment that we apply tension, then stress at this surface will be, what is that? Compression, I can apply compression, but when I try to apply tension, what is the stress at this surface? Zero. Okay. So that is the problem for this kind of loading condition. That's the reason why I said force dynamic triaxial test. Then we got to do the dynamic test. So people figured out this way. Hey, this one will not work. Actually, initially people tried to apply the dynamic stress this way, and they figured out, hey, it's not correct. And we know that people are smart. Sigma 3, sigma 3, sigma 3, sigma 3. Instead of applying deviatoric stress top and bottom, how about applying stress along this way, delta sigma, and it will be high and low. Okay, this figure may appear a little bit different in some literatures, but it is enough easy to understand it this way. Okay. Our purpose is to cause tension along this way, right? Okay, Alex, can you see this figure? Our purpose is we want to cause tension along this way. Then think about how come this loading mechanism will cause the tension along this way. First thing is, let's say we increased our lateral stress. Then what happened to the deformation along this way? It will be increased. It's not a kind of direct tension, but anyhow, anyway, we cause some kind of tension along this way using the Poisson's effect. Okay. It's not true tension. So people call it actual deformation along this way is tension, but it's not true tension. We call it, or people call it, extension. Then what you do is you can reduce delta sigma, and it will be shortened. So there is a kind of maybe fake compression. But we don't say fake compression. We just distinguish tension and extension this way. Okay. So that is the correct dynamic triaxial test. So when you actually repeat this kind of loading cycle for triaxial sample, you will obtain this kind of core pressure build up at each cycle. Then finally you can see liquefaction. Okay. One loading cycle, it will build up power pressure this much. Another loading cycle will build up the power with additional power pressure, then finally the soil will liquefy. In the triaxial sample, triaxial cell, when your soil liquefies, you can immediately see it. How you can see it? You have triaxial sample, right? If that liquefies, shear strength will be eventually 0. That means in your membrane, your soil just becomes the some kind of liquid, and it will collapse. Okay. And for Nathan's case, he got to do some liquefaction test, but we don't have the dynamic loading system. So what he's trying to do is he will prepare a box. He will put the loose sand, saturated loose sand in the box. He will cover it, and that cover should be watertight. Because in here, if the water can escape, it will not liquefy. So you need to cover it. It should be watertight. We got to apply some kind of stress. What we will do is we will use Dr. Irvin's shake table. You know what is the shake table, right? There's a small table in her lab. You can shake it this way or this way. So we will try to cause this way vibration. This one is a kind of tension, compression, vibration. This one is a kind of shear vibration. And we will install a piezometer. Then when we have pore pressure build-up, then this piezometer will catch the pore pressure. So we can see that our pore pressure is increasing. We will also apply vertical stress. We will see whether we will build up the pore pressure. Okay. So this one is called shake table technique. And then you may wonder, hey, which technique is the better technique? This one is the better technique. Then why people use dynamic triaxial or other testing technique? Usually this technique is a lot more expensive than the other techniques. But the good thing for our case is we already have this facility, shake table facility, so we will just use the existing facility. Then probably end of the semester, Nathan should finish at least one test, and he got to make us a presentation.
Oh, I'll do more than one test by the end of the semester.
3?
Yep.
Okay. 3 will be even better.
If you were to draw a cross section, like the void ratio of the box, is it? I mean, it's all the way full to the top. Of the
It
glass.
does not have. I mean, your material should not completely fill the box. Maybe, let's say, the current height of the box is somewhere
8 inches.
8 inches. Maybe we can fill the sand about 6 inches. Put the top cap. Just make sure the top cap should be watertight. Okay. And anyhow, from those tests, we can really mimic the liquefaction. Then another nice parameter that we will obtain from those tests is we can obtain dynamic shear strength of soils. The reason why we do the triaxial test typically is to obtain the strength of the soils, right? And using those tests, we can obtain dynamic shear strength of the test. We need those numbers to actually figure out whether our soil will liquefy or not. And then I think we can talk about liquefaction evaluation procedure. The first thing is you need to understand this feed. depth, shear strength, or shear stress. Okay. What should be the shear strength profile of our soil here? Again, there should be the sandy soil. Sandy soils has 0 C. Then our shear strength equation should be sigma prime tangent phi. As the depth increases, our sigma prime will be increased linearly. This phi is the constant. So we know that our shear strength will increase linearly from 0 to something like that. Okay? Okay. Let's say this one is the shear strength dynamic. Okay. Then let's think about shear stress caused by earthquake motion. Shear stress caused by earthquake motion. Okay. And another thing is, we do not know whether shear stress caused by the earthquake motion is this kind of linear or not linear. To make it general, we will say it's not linear. So I will say shear stress caused by the earthquake will go this way. Caused by earthquake. Earthquake vibration. Okay. Then, conceptually, what we can know is, again, this one is our shear strength. This one is the shear stress caused by earthquake vibration. Then we know that somewhere here, is this the zone that shows possible liquefaction, or this is the zone that shows no liquefaction?
Liquefaction.
The zone of possible liquefaction, because shear stress caused by the earthquake is higher than the shear strength of the soils, right? Okay, so I would say this one should be zone of possible liquefaction. Okay, so now we understand the concept. That means you do whatever analysis based on whatever technique that you know of. If your shear stress caused by the earthquake is higher than the shear strength, we can say we may have the liquefaction. Okay. Then the next question is, how can we define this line and this line? To figure out the detailed procedure, you need to read this article. Sid and Idris, 1971. Simplified procedure for evaluating soil liquefaction potential. There should be Journal of Soil Mechanics and Foundation Engineering, ASCE, Volume 97, number SN 9. Start with page 1249. And this 127. Just is missing. Assumption. Think about a rigid soil column. Okay, rigid soil column that has depth h and unit weight gamma. Okay. Then the vertical stress acting at the bottom of this soil column should be somewhere here at the bottom. Vertical stress should be gamma h. Okay. When this soil is subjected to earthquake vibration, let's say horizontal vibration, and when you have horizontal vibration, again, motion is this one, it should have certain acceleration, right? So we will say that acceleration is A. Again, horizontal acceleration. And earthquake vibration is a kind of random vibration. So each time, each vibration will cause different acceleration. So we will just pick maximum acceleration, horizontal acceleration. You don't ask me why we choose max, why not average. I'll talk about why we chose maximum acceleration a little bit later. Then think about maximum shear stress caused at the bottom of this soil column. Okay, maximum shear stress. Let me write down the equation first, and you may be able to find out the reason why immediately. Get gamma h A max over G. Can you figure out, or can you understand this expression?
You got the
Okay, then forget about this one. This gamma h is the vertical stress, right? Okay, vertical stress, and let's say A max is 0.2 G. Then this A max divided by G is 0.2, correct? That means in that case, our shear stress is 0.2 times the vertical stress. Does that make sense? Okay. Then so far the concept was not really dynamic concept because In this equation, we assume dynamic relationship is really the same as the static relationship. And we will modify this expression to consider some uncertainties in dynamic relationships. I would say tau max dynamic will be gamma d times tau max. This tau max. This gamma d is just the correction factor. Usually, I would say correction factor. And how to find out this correction factor? There should be figure 4 from that reference, Sidi and Idris. Maybe 0.7, 0.8. Again, that's the empirical correction factor. Okay. Again, the reason is this relationship is the one that we borrowed from static condition. So we actually reflected the dynamic condition. Or maybe you can say we just borrowed the equation from static condition. We don't know whether the same relationship can be used for dynamic condition. So we just added up some correction factor for dynamic condition. Okay? Then when we plug in this expression in here, then we can rewrite it here. Gamma d correction factor times gamma h A max over G. Don't be confused with this gamma d and this gamma. This gamma is the unit weight. This gamma d is the correction factor. I don't think this gamma d is really the proper symbol here because it can cause the confusion. But this gamma d is a kind of universal symbol there. Okay, so we have to accept it. And the next. So far we use the A max peak acceleration here. Okay. When we have earthquake vibration, we will have only one peak acceleration. Then we may want a peak acceleration, but we do have some other vibrations too. Then how can we incorporate other vibrations? So it may be better to use the average acceleration, right? And we say tau average dynamic. Now you will understand immediately why we learned this number in the previous class, 0.65. Gamma d, gamma h over A max over G. I think now I don't have to explain why this one is 0.65. We all accept this number, I guess. Actually, that's the whole reason why we spent the time in the previous class to figure out why 0.65 is there. Again, if you want to use 0.85, you got to develop the whole procedure again, but it's not worthwhile. So I would say this is equation 1. Again, this is the shear stress caused by the earthquake. Okay? This is the shear stress caused by earthquake. Okay. If I show the shear stress in this figure, there is really this one. This line should be equivalent to equation 1. The shear stress caused by the earthquake. Then let's think about dynamic shear resistance or shear strength. Okay. Dynamic shear strength. Again, don't forget that our shear strength equation can be C prime plus sigma prime tangent P prime. But for sandy soils, this C is about 0 or equal to 0. So our shear strength equation is sigma prime tangent P prime. Then I will rewrite this equation in terms of tangent P prime. Tangent phi prime should be tau prime over sigma prime. Okay? Okay, tangent phi or phi itself is a unique soil parameter. Phi can be 30 degrees, 20 degrees, whatever, right? So I will write one equation, just conceptual equation in here, tau prime over sigma naught prime. Then may cause liquefaction. Should be sigma. Okay, this one should be dynamic. Dynamic C over 2 times sigma naught or sigma B C over 2 times sigma A. Again. This tau is usually called dynamic shear strength. Shear strength. Again, this equation is nothing but shear strength divided by normal stress. That causes liquefaction. But again, this one is still, physical meaning of this equation is still really the same as tangent T prime. Whenever you have shear strength divided by normal stress for sandy soils, this result is really the same as tangent P prime. Okay, tangent P prime. And we have this sigma D is, this guy is dynamic deviatoric stress or deviator stress. What's the relationship between the deviator stress and shear stress in two-dimensional condition? When you plot the Mohr circle shear stress, normal stress, this is the shear stress, right? Radius, that is what? Sigma 1 minus sigma 3. Deviator stress is the diameter. This one is deviator stress, that is what? I'm sorry. Shear stress is sigma 1 minus sigma 3 divided by 2. This diameter is the deviator stress, that is sigma 1 minus sigma 3. So deviator stress is really 2 times the shear stress for two-dimensional condition. So I just changed this one. This shear stress is 1/2 the deviator stress. So essentially this one and this one are the same equations, right? Then this one is the field equation. Still the deviator stress, dynamic deviator stress. And instead of this sigma naught, we replaced it to sigma A. and we put the correction factor. And what are those? Sigma A is ambient initial ambient pressure. Okay. Again, this sigma A is not exactly the same as this sigma naught. That's the reason why we put the correction factor. Okay? Correction factor. How do we obtain correction factor? That should be obtained from figure 8 in Cden Idris. You may wonder, why do we need to have those correction factors? The whole reason is dynamic behavior is not very simple. So they try to find out an empirical equation so that we can use it easily. That's, instead of exactly the same concept, they just provided a correction factor to mimic dynamic condition. Then from this one, this relationship, what we can do is, hey, dynamic shear stress should be this one, sigma dc over 2 sigma a times sigma r times sigma non prime. Correct? I mean, I just rewrote this equation in a different format. I will say this is equation 2. That is dynamic shear strength. Okay. Again, as always, this dynamic shear strength of the sandy soil should be the function of the depth that is shown as the this pressure. Okay. Then when we go back to that figure, equation 2 will represent this straight line. Okay. That means when we evaluate liquefaction susceptibility or liquefaction potential, we can say this one. Okay. If shear stress in equation 1 is higher than or equal to shear strength in equation 2, then what should be the consequence?
Liquefaction.
We have the liquefaction. Any questions about how we can evaluate liquefaction susceptibility or liquefaction potential? This one is actually the classical procedure for the evaluation of liquefaction susceptibility. And after their research, their approach was improved. And nowadays, we have similar techniques that has a little bit more corrections. We also have some techniques, actually those techniques are also proposed by Cden Idris. It's something like this one. You may think of soil strength represented by SPT blow count, N, or maybe you can say N60. And this is the ground acceleration. It depends on, you may use A average. Many times people just pick the peak acceleration because it's easy. Okay? Then Cden Idris and many other people just collected a lot of field data. They figured out, hey, when SPT blow count is, let's say, 30, ground acceleration was somewhere 0.15, whatever. Then they collected this data. This data means, okay, and they analyzed the data and they figured out, hey, this data, that means for the, let's say, N60 somewhere 25, it was liquefied. This point was liquefied. This point was not liquefied, So that from this empirical data, they figured out, hey, above this line, liquefied, below this line, not liquefied. Very easy chart. You don't have to go through the detailed procedure. So this technique is also used. And instead of n sub 60, you can also collect the same data based on con resistance, con-tip resistance. Liquefied. Not liquefied. Easy. And nowadays, people try to improve these techniques, and they just massage those numbers, and some people say instead of Amax they say CRR, some people say DRR, whatever. But eventually the fundamental idea of those CRR or DRR is based on this or this concept. You have to figure out what are all those CRR, DRR.
Cyclic stress ratio.
Yeah.
Dynamic stress ratio.
Questions?
Yeah, so that area between the two curves over there, that's the liquefaction potential.
No, it's not called liquefaction potential. This one is called liquefiable area. Liquefaction potential is not a single number or a single region. Liquefaction potential is something like, okay, if you have, this soil has high liquefaction potential, that means this stress is actually higher than this strength, or this stress, shear stress is very close to this one, then you can say it has high liquefaction potential. You don't say liquefaction potential is 0.8, 0.9, whatever.
Mm-hmm.
If this one is a lot lower than this one, you can say low liquefaction potential. Any other questions?
How many different ways are there to figure out the liquefaction potential? Over 20?
I don't know, but at least, I would say at least 20 different approaches. But
It's like, I mean, just of those ideas right there. I mean, could you not just do the like SPT test and then also take a, we'll have the bore log and say you can tell. I mean, if you know if it's going to liquefy, then you could correlate the classification of the soil to if it liquefied, and then you would.
oh yeah.
I mean,
There are some indirect approaches too. Okay. Actually, after you read that reading assignment, then I will talk about some indirect approaches to figure out whether our soil is liquefiable or not. For example, the very first requirement is our soil should be loose sand deposit and water table should be high. If there's no water, then there's no liquefaction. Okay. Also, the gradation is also one of the governing factors. This kind of condition is very poorly graded materials. If we have some smaller particles they are filling with the void, it's a lot more difficult to move around, right? So well-graded materials typically has lower liquefaction potential. Poorly graded ones will have higher liquefaction potential. Also, it also has something to do with the depth. When you see this figure, somewhere down here, it shows that shear strength of the soils is higher than the shear stress caused by earthquake motion, right? Then no liquefaction. So depth has some effect. Void ratio, I did not talk about the void ratio, but you can expect when we have the liquefaction. High void ratio soil or low void ratio soils.
So what depth
It
can
depends.
liquefaction happen at?
High void ratio or low void ratio soils? High void ratio one. High void ratio one means loose ones. What do you say?
So what depth can it happen at?
It really depends on the soil types, but rule of thumb, it says rural here, right? Do you see any number?
Around 30 meters.
About 10 meters, 30 feet. Okay. If the soil is usually deeper than 30 feet, we hardly have the liquefaction.
Is that because of the confining pressure?
Because of the confining pressure. High confining pressure means if you have already a high confining pressure, it's not really easy to move those particles. But time to time, you will see some people, even at somewhere 300 feet, there were some liquefactions, but there is no proof usually. They just suspect, okay, because we have such and such behavior to our structures, there should be some liquefaction of our soils deep down there, especially those I think there is the nuclear power plant somewhere in Savannah River.
Mm-hmm.
Those people are talking, suspect the deep liquefaction. I think there's the homework. No homework this time. Okay. But I will put the exam right after this class in the blackboard. But you also think about the term paper. Okay. Term paper will also take the 100 point. Think about what you will do as the term paper. Then probably after the exam we will talk about who will do what for the term paper.
Do you want me to come get the card from you so I can order that?
Yeah.
Yeah, so it was a little over 700 altogether, and that included the